All right, guys. In this series of videos, I'm going to be going over the free response test that was the 2015 international exam. Okay, so this was the free response that the international students took. And so I just want to go through it. And what I'm going to do is kind of go through the the questions and show you kind of the notes I made as I go through the questions. Just things like this means look out for this, watch out for this. Just little notes that I make, kind of annotating the question, and then I'm just going to go directly to the scoring guide and show you what the right answer is, what College Board was looking for. So we'll start with question one, but this will probably be a multi-part video, so we'll just go in order. But so I just want to take it question by question, go through different things, highlight different things that you should be looking out for when you're taking the test, and just all that good stuff. Um, and maybe other ways you could think about a question that would still get you credit, even though it's not on the official College Board scoring guide. It's still, there's still might be a different explanation that would still give you credit for a certain question or something like that. All right. So let's just dive into that practice test. All right. Yeah. All right. So again, just to highlight, understand how the test is structured. Okay, the free response portion of the test, you get 105 minutes, an hour and 45 minutes. Okay, it's 46 points total. All right, and this is half of your AP score. The other half of your AP score is based on your multiple choice portion of the test. Okay, so if we look at the way the free response is structured, there's 7 total questions. The first 3 are longer questions where you're going to have maybe 10 different prompts per question because each one is worth 10 points. So if you have 10 prompts, each prompt is just worth a point. If you have maybe like 8 prompts, then maybe a couple of those prompts will be worth a point. Usually maybe 1 point for correct answer and then 1 point for correct explanation or something like that. So you should be able to go through it and say, okay, well, there's 8 different things here. So 2 of these things are going to be worth 2 points, or there's 10 different things here. So each one is just going to be worth 1 point. So if they ask you for, do you agree or disagree and justify? Well, if you know it's only 1 point per question, then you have to get both the agreement part or disagreement part of it right and the explanation right to earn that 1 point. Okay. So just kind of understanding how they boil things down might help you. Is it worth my time to guess on an explanation or not? That kind of thing. But you can get 10 points apiece for questions 1 through 3. So that means 30 total points. So 30 out of the 46 points are just in questions 1 through 3. Okay. And they're telling you to budget around 23 minutes per question in question 1. So 23 minutes for question 1, 23 minutes for question 2, 23 minutes for question 3. When you get to 4, 5, 6, and 7, you're going to notice that there are a lot shorter questions, maybe 2 prompts, maybe 3 prompts, maybe even 4 prompts, but each one of those questions 4 through 7 are only worth 4 points apiece. And they tell you should budget only about 9 minutes. All right, so hopefully you brought your stopwatch with you to the test, and hopefully you're kind of keeping track and saying, okay, well, I've spent too much time on question 1. I got to move on to question 2. And another thing you'll notice is, I think, from the way it looks on most of the time when I go through these different free response tests, is questions 6 and 7 are usually really easy questions. So that might be an easy 8 points for you to get, question 6 and question 7. But a lot of students don't get those points because they just ran out of time. They spent too much time on question one. They spent too much time on question two. And so by the time they get to question seven, it might be a really easy question and they know how to answer it, but they just run out of time, or they're moving too fast at that point because they know they're going to run out of time and they make silly mistakes. So, budgeting your time, just normal test taking skills, not chemistry skills, just test taking skills, reading comprehension. That's, I would say, 80% of the battle. And then 20% is like, hopefully you remember the chemistry you learned this year, right? So just to kind of look out for that stuff. All right, so let's go to question one. So right off the bat, boom, question one, I have two reduction reactions. I know they're reduction half reactions because electrons are reactants, right? So these are reduction potentials. I'm thinking that as soon as I see this, if I'm going to make a galvanic cell, a spontaneous redox reaction, I would end up flipping this reaction. I would reverse this reaction. So it would really be this being oxidized and this reaction being reduced. Because if I were to reverse this one, I would end up with a negative cell potential. So reversing this one gives me a positive cell potential, right? So just, the first thing I notice, right? And then boom, it says galvanic cell. So I know, yep, I'm going to reverse that one because I need a positive overall cell potential. Okay. And so part A is just asking, write a balanced equation for the overall reaction that occurs. So boom, all I have to do is flip this reaction and then add the two half reactions. So I'm going to reverse this reaction. I'm going to add these two, but remember when I add these two, number of electrons has to be equal to each other. So I know I got to multiply this equation by 3. So all these coefficients will be 3. I'm putting these two things on the reactant side and these two things on the product side. Notice you're going to end up with some H pluses canceling out as well. And you're going to end up with some waters canceling out. Not all the water is going to cancel out. But if we multiply this through by 3, I'm going to end up with 12 H pluses on this side and 12 H pluses on the opposite side. So all the H pluses will cancel out, all the electrons will cancel out, and then we just have to add it up. And then if I just make this a positive, and I add these two numbers together, remember, I might triple this, but that doesn't mean change this value for cell potential. So this plus positive that is going to be my overall potential. And that's what part B is about. All right, so let's just check the scoring guide. All right, so yep, there's my overall balanced reaction. So again, I reversed this one and I multiplied this one by 3. I canceled out what could be canceled and I got that. And then for part B, I just took the opposite of negative 0.085, right? I flipped the sign and then I added it to, so positive 0.085 is my oxidation potential. 1.299 is my reduction potential. I add those up to get my overall potential. All right, so that's A and B. All right, see, it says a 10 milliliter sample of this aqueous alcohol is put into an electrochemical cell. The cell produces an average current of 10 amps. Remember, amps are coulombs per second for 20 seconds. And remember, it tells you that amps are coulombs per second. So, on your formula sheet. So don't sweat it if you forgot, but that's something to know. At which point the ethanol has been totally consumed. Okay, calculate the charge in coulombs that passed through the cell. So remember, all you have to do is amps times seconds will give you coulombs. So CI, all I have to do is take my 10 amps, or 0.1 amps, multiply it by my 20 seconds that they gave me, and I get 2 coulombs. Okay. And then it says calculate the initial concentration in the solution. Okay. So let's go back up to our balanced equation, right? For 1 mole of this to react, it produces 12 moles of electrons. So we just figured out the how many coulombs, And then remember, we can use Faraday's constant to get moles of electrons, and then moles of electrons to get moles of this that we initially had. And then if we divide it by the the old volume, the original volume of the solution, that'll give us our molarity. Okay, so we would take our 2 coulombs, divide by Faraday's constant, that'll give us moles of electrons. The mole ratio of the ethanol to moles of electrons was 1 to 12 in this case, so that gives us how many moles we had, and we divide it by 0.01 liters, and that gives us our molarity. All right, and notice this was a 2-point question. 1 point earned for doing the kind of electrostoic part of it to get moles of ethanol, and then 1 point earned for figuring out the correct molarity. So knowing to divide by 0.01 liters at the end there, okay? Now, here, the next part of the question says an alternative approach to determine the concentration of ethanol in a solution is based on the reaction represented below. And, I was thinking they gave us colors here. And so as this reaction proceeds, the solution is going to be going from orange color to blue-green color. So the solution is going to be absorbing different color light as the reaction goes. So I was thinking maybe colorimetry, spectrophotometry, right? Beer's law. But let's find out if I'm right about that. But that's the only reason I wrote colorimetry there. Yeah, boom. And then we have absorbance and time data. So we might be thinking colorimetry. Okay, so it gives us this whole explanation. And so it says calculate the concentration of the dichromate ion at 1.5 minutes. Okay, so we were measuring the absorbance of this wavelength, which is being absorbed by the dichromate ions. Okay, and notice again, if we go back up to the original reaction, as the reaction proceeds, we're consuming the dichromate ion. So as the reaction proceeds, we're losing dichromate, so the concentration of this, so the dichromate's going to absorb less and less light. So if we look at, the chart that they gave us, we notice that the absorbance is decreasing, and that's because as the reaction proceeds, we know the dichromate concentration is decreasing. Okay, so just real quick, just some notes I put up here. I figured out that dichromate was first order kinetics. Did they say that? No. But what I did was, remember, when you're given amount versus time, whether it's concentration versus time, absorbance versus time, partial pressure versus time, remember, try to find the half-lives. So 0.78 divided by 2 is around 0.389. So that's one half-life, and it took 3 minutes. And then 0.389 divided by 2 is close to 0.194. So the next half-life took the same amount of time. So notice the half-lives are remaining constant, and that is a sign that the dichromate ion is following first order kinetics. So I just made that note because I just wanted to, that's one of the first things I check for. Okay. There's a few ways you could do this one. You could use Beer's law, but if you're going to use Beer's law, you're going to have to find molar absorptivity, or you could just make a proportion because absorbance and concentration are proportional to each other. So, because you were given the initial molarity of the dichromate up here, so you could say, this molarity divided by this absorbance equals X molarity divided by this absorbance, because we want to know the concentration at 1.5. So a couple ways you could go about it. Let's see what they did. Yeah, so notice the first one, they made a proportion. So they figured out the molarity was 7.1 times 10 to the negative 4. But remember, you could also do Beer's law, A equals ABC, but you're going to have to calculate the molar absorptivity. So, one way to calculate the molar absorptivity is graph this and find the slope of the line, and that's the molar absorptivity. Or, because, again, we have those initial conditions, we have an absorbance value and we have the initial molarity, So we have the concentration, we have the absorbance, and we have the path length. It was 0.5 centimeters was the path length. We can plug that into Beer's law and solve for A, lowercase a. And so then we get a molar absorptivity. And now that we have the molar absorptivity, now we can go back to Beer's law and solve for C, now that we have lowercase a. And notice, either way, we got the same answer, 7.1 times 10 to the negative 4. And you don't have to use scientific notation. You could say, 0.00071 if you wanted to, but probably easier to use scientific notation. Okay? All right. The student runs a second trial, but this time uses a cuvette that has a path length that's 1 centimeter. So the original path length that used for this data was 0.5. So understand, if you double the path length, you're going to end up doubling your absorbance value, because more light will end up being absorbed because more light has to travel, or the light has to travel through a longer distance through solution. Describe how the experimental setup should be adjusted to keep the initial absorbance this. So if you want the initial absorbance this, you would have to you would have to cut the initial concentration in half, right? Does that make sense? All right. I know I'm asking nobody that question here. Here, let me try to. Sorry. Let me fix something here. Is that gonna work? Okay, yeah. All right, so yeah. If the path length is doubled, the molar absorptivity is constant. The initial concentration must be halved to keep the absorbance the same. There you go. All right. So we had to cut the concentration in half because we doubled the path length in that experiment. Okay. For the concentrations of the reactants used in the experiment, the rate of the reaction can be written as follows. So rate equals K times the dichromate concentration raised to the Y, where K observed equals K times the concentration of ethanol raised to the first power. Explain how the experimental data indicate that the reaction is first order with respect to dichromate. And so that's where the half-life, right? So the half-life was constant. So dichromate is first order. Okay. So absorbance is proportional to concentration. Absorbance is halved after 3 minutes and then halved again after another 3 minutes. Thus, the half-life of the reaction is constant, so the reaction must be first order. There you go. You could also graph the natural log of the concentration of chromate, or you do the natural log of the absorbance of chromate versus time and show that it's linear, but I feel like that would take too long. So again, that's why the half-life, getting good at, so understanding that if it was zero order, the half-lives would have gotten shorter, or if it was second order, the half-lives would have gotten longer. But in this case, because the half-lives remain constant, we know it's first order. That's really what you need to know there. Okay? All right. So, okay. So that was question 1. And then again, this was just kind of the work for question 1, D. Okay. All right. So let's move on to question 2. So question 2's got a lot going on, right? Like when you see this, you're like, do I really want to read all this? So it has a bunch of different reactions and stuff. It's asking about ionic compounds. So what I would do, the way I attack this question is I don't look at this right now. I read what the questions are asking, and if I have to reference this, that's when I'll come back and reference it. Because maybe I don't need all this information, okay? Or at least right off the bat, right? My goal is to try to get as many points as possible, and I'm a slow reader, and so I know that's going to start confusing me, and I'll get lost in it. And so really, I want to just keep it simple and see what the questions are asking, right? So if we look at part A, it says iron 2 oxide and aluminum oxide have similar chemical properties. Some similarities are due to the oxides having similar lattice energy. So remember, lattice energy is just how strong the ionic structure is, and that's based on how strong the ionic bonds are. Give 2 reasons why the lattice energies of the oxides are similar. So remember, lattice energy is just about Coulomb's law, and there's only 2 things to Coulomb's law. The size of the particles, so the smaller they are, the closer they can get together, the stronger the attraction, and then also the overall charge. Well, we have the same charged ions. Iron is 3 plus, aluminum is 3 plus, oxide's 2 minus, oxide's 2 minus here. So same charge, and aluminum 3 plus and iron 3 plus are similar in size. Okay, so similar size, similar distance between ions, and similar and same charge. Okay, so let's see how the scoring guide has it. Iron 3 plus and aluminum 3 plus have similar sizes, yep, and they have the same charge. There you go. Boom, Coulomb's law. But notice we only got 1 point. Oh, no, 1 point for each region. So this was 2 points. Okay, good. All right, if we go to part B, they give us the KSPs for so iron 3 hydroxide and aluminum hydroxide. Remember, they have the same ratio, right? This is a 1-to-3 ratio. So what would be our KSP shortcut? What, KSP equals 27x to the 4th. So if we needed to calculate molar solubility, right, we'd be KSP equals 27x to the 4th, and we'd solve for x. But when they have the same ratio, you can tell which one is more or less soluble based on just their KSP values. So aluminum hydroxide is more soluble than iron 3 hydroxide, because we're comparing 10 to the negative 33 to 10 to the negative 38. So aluminum hydroxide is going to be more soluble. The KSP values of iron hydroxide and aluminum hydroxide are given in the table. 1 gram sample of powder and of iron 3 oxide and a 1 gram sample of aluminum hydroxide are mixed together in 1 liter of distilled water. Which ion, iron 3 or aluminum 3, will be present in a higher concentration? Justify. So more aluminum is going to be able to dissolve because it's more soluble. So it would be aluminum 3 plus. And because we're comparing the KSP values there, and we're allowed to compare the KSP values. Well, they tell us to compare the KSP values, but we know that we can, and we don't have to worry about molar solubility. Okay. So aluminum has a higher presence, and it's because they have the same ratio. They said stoichiometry, it's the same thing. They have the same ratio, right? They have the same recipe, but has a greater KSP. All right, great. All right, write a balanced chemical equation for the dissolution, so just aluminum hydroxide dissolving in water. And remember, if you got part 1 wrong, if you said iron 3 hydroxide for some reason, you know, as long as you wrote this reaction with iron 3 hydroxide instead of aluminum 3 hydroxide, you could get full credit for part 2. All right, so all we're doing is that. So just aluminum hydroxide dissolving in water. Okay, that's it. Okay. Students were asked to develop a plan for separating aluminum oxide from a mixture of powder iron oxide and powder aluminum oxide using chemical reactions and laboratory techniques. So these ones here. So here's our mixture, right? So I guess like the first thing we do is add it to water, and then it'll form this. Then we can take that and add it to sodium hydroxide, and the aluminum hydroxide will dissolve, but the iron 3 hydroxide will stay a solid. Then I guess we could filter out that, and the this would go through to the filtrate, and this solid would stay behind in the filter paper. Then we could mix it with HCl, and these reactions would happen, and we would get iron 3 chloride, aluminum chloride, and aluminum hydroxide solid. And then it says if we heat aluminum hydroxide solid, that'll give us aluminum oxide. So if we take what we're given here and we react with HCl, everything will be dissolved in solution except for solid aluminum hydroxide. So if we filter it and collect the solid will be aluminum hydroxide, and everything else will be in the filtrate. So we'll just take that solid aluminum hydroxide, heat it up, and then we will only have aluminum oxide. So that would be the way to step it up, okay? But anyway, so one student proposes that aluminum oxide can be separated from a mixture by adding water to the mixture and then filtering. Explain why this approach is not reasonable. This would only work if aluminum oxide was much more soluble than iron 3, but it's not. So, they are very much both insoluble compounds based on their KSPs. So that's not going to work. All right, so let's see. The approach only works when there is a significant difference in water solubility between the two substances. There you go. All right. All right, so this is, it gave you some of the steps for figuring out how to isolate the the aluminum oxide. And so we have to fill in the remaining steps here. Now, I want you to notice in the past, in other exams, they've had questions like this where you don't necessarily need to have this many steps, okay? But let's, again, if we go back to the thing, it says, filter out the iron 3 oxide and save the filtrate. So that iron 3 hydroxide. So they tell us this step and then filter it out, okay? Then what do we have to do? So the next step that we're going to write down is react the, what is it? Let me see, what did they give us? Yeah, so it said add the hydroxide to form this, okay? And then filter it out. And then so now we'll collect the filtrate. So all we'll have is this, okay? Then it says react it with then we'll react it with HCl. We'll react the filtrate with HCl. All these reactions will happen. So any iron hydroxide that's in there will react. The aluminum hydroxide will react, and the sodium aluminum hydroxide will react. And what it'll form is aluminum hydroxide solid, but everything else will be dissolved. Then we'll filter that, but we'll collect the solid, and then we'll heat the solid up, and that'll be that. All right. So those would be our steps. Let's see what the scoring guy says. Add HCl, okay, until the precipitate forms. Filter out the solid, heat the solid. There you go. All right, we did it. All right. Let's keep on rolling. All right. The student recovers 5.5 grams of aluminum oxide from a 10-gram sample of the mixture. Calculate the percent aluminum by mass in the mixture of the two. So we could, if we did 5.5 divided by 10, that would give us the percent of aluminum hydroxide in the mixture. So we have to do a little bit of stoich here. We have to figure out how many aluminums, how many moles of aluminum or how many grams of aluminum we have, and then divide it by the 10 grams there. Okay, so we would do the 5.5 grams divided by the molar mass that was provided for us, times 2/1, because there's 2 aluminums for every 1 mole of aluminum oxide, times the molar mass of aluminum, and that would tell us we had 9.2 grams, or 2.9 grams of aluminum, and the whole sample was 10 grams, so 2.9 divided by 10, we got 29% aluminum. Okay? All right. All right, so that's questions 1 and 2. I'll come back in the next part of the video to start on question 3.